Hello students, and welcome to today's SHS3 core mathematics lesson. Our topic for our revision today is plane geometry 2. I'm Asiedu, Menlah, your facilitator for today. Now let's look at the lesson objectives. Now by the end of the lesson, you students should be able to state the plane geometry 2 theorems. And then also you should be able to apply the theorems to solve simple problems. Now, in any lesson, you need what we call a relevant previous knowledge. That is knowledge you have that should be able to help you to build on. Now, for plane geometry 2, what you need is first that you should be able to draw a circle and label the parts. It's very, very important for you to be able to move on with plane geometry 2. You should be able to draw a circle and label the parts. I'll be looking at it very soon. And then also you should be able to know and apply the theorems of plane geometry 2. It's expected that to be able to understand plane geometry 2, you should have gone through plane geometry 1. So these are the two relevant previous knowledge we need. Very important. Now let's get into the lesson as it is. So I'm going to start with the first relevant previous knowledge, which is your ability to draw a circle and label the parts. I know you've done it. This is something you should have done even in basic school, in JHS, and even at the early stages of your mathematics in Form 1. But for the sake of this lesson, I'm going to quickly refresh our minds with that. So you have a circle, and naturally this is what we call the circumference. Then of course you have your center, and then as you know by now, the circumference is the whole length of the circle. Now, any part of the circumference is what we refer to as the arc. So, for example, from this end all the way to this end would be what you call your arc. And then also, you know by now that any point, any line from the center of the circle to any part of the circumference is your radius. Then any line from any part of the circumference through the center, through the center to any other part of the circumference will naturally be your diameter. Now, if you have more than one radius, we call it radii. I'm sure you know that by now. Now, the area between any two radii, for example, what we have here is naturally what you call your sector. Then, of course, we must also know that a line from the circumference to another part of the circumference which does not pass through the center is what we call the chord. So that the area between your chord and that part of the circumference, which I've already described as the arc, for example, this area is what you will call your segment. And that is very, very important. Please take note of that because I will be coming to that part. Right, so basically these are your parts of a circle. Very, very important. Very, very important. But let me also draw your attention quickly to some two very important things, especially with your circle. One is that when you have your circle, two of them, so let me read. Now, when you have, say, a circle with a center, now when you have radii, naturally you divide the circle into two sectors. You divide the circle into two sectors. And you could see in this case, for example, that the sector we have here, that is the sector is basically an area between two radii. So this area is actually a sector. This is also a sector. But you notice that this one is bigger than this one. Now the bigger one we call a major sector. And then the smaller one we call a minor sector. Now similarly, if you have a circle with a center and you had a chord, for example, from what I have here, again you divide the whole circle into two, what we call two segments, so that the smaller one, the bigger one, we'll call a major segment, and the smaller one we'll call a minor segment. So please take note of this. So these are some very vital information concerning circles which we need to be able to build on and get into our plane geometry too. I want to believe they are very, very clear to you now. Now let's quickly get into the theory. Remember, we are looking at plane geometry too, and I'm going to try and take you through the properties, at least for this particular lesson, take you through the properties, or what we call the theorems. And I'll be taking you through almost about 9 or 10 of them, and I'm going to be as fast as possible so that we can finish. So the whole lesson will be focusing on the theorems, and then our subsequent lesson will take time to look at typical examples concerning them. But I'll try as much as possible for each theory that I raise. I'll just give you a simple example on it so that it will clarify the theorem. Okay, so let's move on. Let me erase what I have here. I want to believe that at least you've been able to write them down. So I'll quickly take them off and then start with the theorems. So let's go. Okay, so first theorem. So theorem 1. So let me put the theorems. And then I have the first one. Now what does the first one say? The first one says the angles a chord or an arc subtend at the circumference in the same segment of a circle are equal. If I have to write it so that you can quickly write them down, I'll say that the angles a chord or an arc subtend at the circumference in the same segment of a circle are equal. So that is our first theorem. Very, very important. An arc subtends at the circumference in the same segment of a circle are equal. Now, what do we mean? What we mean, now you notice that I mentioned chord or arc. Now let me use the diagram to explain it better. So what I'm saying is that if I have a circle and with a center, right, we are saying that the angles a chord or an arc subtends at the circumference. So if, for example, I have a chord here, now when I talk about a chord, I'm actually talking about the ends of the chord. In the actual application, you look at the ends of the chord. So I have a chord. I'm saying that if this chord subtends, the end of this chord subtends an angle here, one here. So you have forming an angle here. Let me call it A. And then this same ends of the chord subtends another angle. Same chord. Now, you notice that I keep using the word subtend. Subtend is a technical word. It's a mathematical technical word, but it simply means form. So when you hear subtend, I'm actually saying form. So it will simply read as the angle a chord or an arc forms at the circumference in the same segment of a circle are equal. So that if I have this angle, which is also B, I can even go ahead and create another one. C. Now, what you have to take note is that the angles we have there, the most important thing is that all these three angles are formed by the ends of the same chord. That is a crucial condition to take note. Now, the second crucial condition to take note is that all these angles are in the same segment. They are not in different. You can see that there is one segment here and there's another segment here. But all the angles are formed in that same segment. And the principle or the theorem simply says that if you have any of such situation, then all those angles should be equal. So we will say that from that diagram, we have A is equal to B is equal to C. All these angles must be equal. Now let me put up a simple example to explain that. So that if you were given, in a typical example, you were given something of this nature. Right, and you were told that, for example, this angle is X, and this angle is, let's say, 53 degrees, and you were asked to find X in a typical question. What we are saying is that these angles you have here, they are formed at the circumference, they are formed by the same chord, which is this particular chord, or sometimes you may not even have the chord there at all. That is why we talk about an arc. So that's why we say we are talking about the angles, a chord or an arc. So that in this case, we are talking about this arc. Or if the chord is still there, whether it's there or not, we are referring to the same thing. Then you can safely say that because of all those conditions are there, you can simply say that your X is simply equal to 53 degrees. So that explains our first theory. I hope it's very, very clear to all of us. Now let's quickly look at the second one. As I said, this lesson is just dedicated to taking us through the the theorems. So that's the first one. Now let's quickly look at the second one. What does the second one say? It says, let me erase the first one and then put up the second one quickly. Now the second one says, the sum of the angles a chord subtends at the circumference. The sum of the angles a chord subtends at the circumference of opposite segments of a circle are supplementary. So you can put it down. So that would be so in this case, it's not the first, but rather the second. The sum of the angles a chord subtends at the circumference of opposite segments of a circle are supplementary. Now, you notice that in the first one, let me pick it up from here. In the first one, we said that one of the things, the conditions we emphasized was that all the angles we were talking about were formed in the same segment. Now, but this time, we are saying that if I have a circle with a center, as I have it here, and I have a chord, and that chord is forming an angle here, for example. Let me call it A. And then the same chord is forming another angle at the circumference. But this time, the angles are not being formed in the same segment, but the other angle is formed in the other segment, which we are referring to as the opposite segment. So, for example, an angle is formed here. The angle is formed here, which I'll refer to as B. Now, what we are saying is that this time, these two angles will not be equal, but they will be what we call supplementary. Now, what do we mean by supplementary? When we say two angles are supplementary, we mean that when you add them up, it gives you 180 degrees. That's when you sum them up, the two angles, you have 180 degrees. So it means that, what it will mean is that in this case, our A plus our B should give us 180 degrees. Very, very important. 180 degrees. So again, I'll quickly give you an example to actually explain, a simple example, as I said. So again, if I have a circle, and I have a chord, and that chord is subtending an angle here, and that same chord is subtending an angle in the other, such that maybe this angle is maybe Y, and the angle here is, let's say, 40 degrees, and you are asked to find Y. Now, this particular question follows this theorem or this property, and so from this you can easily say that your Y plus your 40 degrees should give you 180 degrees. So that Y, from that simple equation, your Y will be equal to 180 minus 40. So that Y will simply be 140 degrees. So that explains the second theorem. Very, very important. Very, very important. Now, quickly, let's look at theorem number 3. Theorem number 3. So I'll pick it up from here again. Theorem number 3. Now, what does theorem number 3 say? Theorem number 3 says the angle a chord or an arc subtends at the center of a circle is twice the angle it subtends at the circumference in the same segment of a circle. Right? Now, let me put it down for you so that you can write it. The angle a chord or an arc subtends at the center of a circle is twice the angle it subtends at the circumference. The circumference. In the same segment, center. Right, so the angle a chord or an arc subtends at the center of a circle is twice the angle it subtends at the circumference in the same segment. Now, what do we mean? Let me use the diagram to explain it and to clarify what we have there. What we are saying is, if I have a circle with a center and I have a chord, or an arc. For example, if I have a chord and this chord subtends an angle, and you remember I said that when I mentioned chord, I'm actually talking about the ends of the chord. In practice, we use the ends of the chord. So if this chord subtends, or it forms an angle at the center, let's say an angle A, and then this same ends of the chord subtends another angle, but this time, although in the same segment, but this time at the circumference. The angle is formed at the circumference, not at the center. We are saying that if you have that situation, then we are saying that the angle formed at the center will be twice the angle formed at the circumference. So it will mean that our A will be equal to twice, that is 2 times the one at the circumference. Now, this is when you know the angle at the circumference and you want to find the angle at the center. On the other hand, if you knew the angle at the center and you wanted to find the angle at the circumference, then you will simply mean that you are finding B. So it means that you will simply have to divide both sides by 2, and it will mean that your B is equal to A over 2, or half of it, depending on which one you want to find. So quickly, let me pick an example. So you could have something of this nature, so that if you had something of this nature, you had, let's say, a Z, and you had 45, or let's say 45 degrees, and you wanted to find Z. According to the principle, your Z is equal to twice that angle there, which means that your Z will simply be 90 degrees. Now, on the other hand, if you happen to have a circle, again, where you have center, and this time you have the angle here to be, let's say, 150 degrees, and then the angle here is, say, W, and you wanted to find W. Again, the principle says that twice the angle at the circumference is equal to the angle at the center. So it means that if I want to find W, I simply have to divide through by 2, so that my W will simply be over 2. So my W will be what? 75 degrees. So that explains theorem number 3. Quickly, okay, so we go to the fourth theorem. Now, what does the fourth theorem say? The fourth theorem says that the angle, the diameter of a circle subtends at the circumference of any of the segments is 90 degrees. The angle, the diameter, sorry, I didn't write the angle. The angle, the diameter subtends at the circumference in any of the segments is 90 degrees. That's very, very important. So what that simply means is that if I have a circle of this nature, let me use the one I've already drawn. I have this circle, and then with a center. Remember, we have introduced a key word here, diameter, and we said the diameter is a distance or a line through the center from one point of the circumference to another. Now we are saying that if that happens, if the ends of the diameter subtends an angle, now whichever segment it falls, that angle should be 90. So for example, this angle will be 90, and normally when we have an angle of 90, we indicate it with that sign. it could also be in this other segment. You notice that for the others, we were basically talking about, most time talking about in a particular segment, but this time we are saying that whichever segment it falls, you are going to have the same situation, an angle of 90. So that's basically about theorem 4. Theorem 4. Now let me quickly pick an example then, so that if I had a circle and I had a diameter and I had an angle here, for example, and I was told that this angle is, say, Q, and that this angle was, say, 35, and I needed to find the angle Q. Now the principle from what we have learned here is that the angle here is supposed to be 90 because it is formed by the ends of the diameter, and here we'll have to borrow another property which we are supposed to know from plane geometry 1. Remember, we are taking plane geometry 1, geometry 2, and I said that for you, one of your previous relevant information you need is the concept of plane geometry 1, which simply means that the sum of the interior angles of any triangle is 180. So going by that, it will mean that Q plus 35 plus the angle here 90 should give us what? 180. So Q plus, from that simple equation, Q plus 125 degrees should give us 180. So our Q is 180 minus 125. So our Q will simply be 65. Great. So that is our fourth theorem. Then, not 65, sorry, rather 55 degrees. Now, quickly, let's look at theorem number 5. Theorem number 5 states that the opposite angles of a cyclic quadrilateral are supplementary. Very important. Number 5. The opposite angles of a cyclic quadrilateral is supplementary, and I've already defined supplementary by saying that it means when we sum them up, it gives us 180 degrees. Now, what does that simply mean? It follows. What it simply means is that now we need to understand what we mean by cyclic quadrilateral. Now, a cyclic quadrilateral, we know that a quadrilateral is any four-sided plane figure, like the square, the rectangle, the rhombus, the trapezium, all of that are what we call quadrilateral because they are four-sided and they are plane figures. Now, when you have a plane figure which is fitted into a circle, that fits into a circle, then you have what we call a cyclic quadrilateral. So in this case, we have something of this nature. I have a square, and not a square per se, but any quadrilateral at all. It could be a square, it could be a rectangle, it could be whatever. But the most important thing is that we have a quadrilateral, so that if this angle is say A, and this angle is say B, and this is C, and that one is D, the concept says that the sum of the opposite angles. So you notice that from here, A is opposite to C, and then B is opposite D. And we are supposed to understand that when we add them, they give us 180. So in that case, it will mean that A plus C will give us 180 degrees, and B plus D will also give us 180 degrees. So that's a very important concept to understand. I hope it's very, very clear. Very, very clear. So now let's move on to theorem number 6. Theorem number 6. Theorem number 6. Now, theorem number 6 states that equal chords or arc subtend the same angles at the circumference of a circle. Number 6. equal chords or arcs subtend equal angles at the circumference of a circle. That's the concept. Now, how do we interpret that? How do we interpret that? Equal chord. What it simply means is that if I have a circle with a center and I have a chord, let's say this chord, and I have another chord, let's say this one. Now, if the length of these two chords are the same, in that case, in mathematics, we indicate that by putting some lines, some small lines here. Now, anytime in mathematics you see something of that nature, it's telling you that the length of this line is equal to the length of that line. We are saying that if this line, which is a chord, actually forms an angle at the circumference, for example here, and we have an angle, say A, and then this other chord is also forming another angle at the circumference, which is say B. Now the property says that those two angles are also supposed to be equal because they are coming from two chords which are of the same length. Very, very important. So please take note of that. Now let's quickly jump to the seventh property, which is more or less similar to the sixth one, but that one goes like this. It simply says equal chords or arcs subtend equal angles at, this time at the center, of a circle, So this will be our seventh principle or our seventh theorem. So how does that come up? It's similar to this one. Let me erase it so that will be faster. What it simply means is that if I had a circle and with a center, of course, and again I had a chord, right? And I had another chord, maybe somewhere there, and this chord is equal to this chord. Then we are saying that when the end of this chord forms an angle here at the center, say A, and the end of this other chord also forms an angle at the center, let's say B. Now the concept says that those two angles are supposed to be equal. So it will mean that A is simply equal to B. So that is the seventh concept. Quickly, let me look at the eighth theorem or the eighth concept. Now what does the eighth one say? The eighth one says the angle between a tangent and a radius in a circle is 90 degrees. The angle between a tangent and a radius. So let me take that one. Write it so that you can put it down. Say 8. The angle between a radius and a tangent in a circle is 90 degrees. Very important, very key, and very key. So what are we talking about here? We are saying that now again I've introduced a concept here, and that concept is tangent. It has not come up so far, and so I have to quickly touch on it. What is a tangent? A tangent is basically a straight line that touches a curve or a circle. A straight line that touches a curve or a circle is a tangent. So for example, if this circle, I have a straight line which is not cutting through the circle or which is not far away from the circle, but it is actually touching the circle at a point, at a certain point. So let's say it is touching it at this particular point, then this line will be your tangent. And here we are saying that, and we know, I've already mentioned radius, which we said is any line from the center to any part of the circumference. But this time, we want the radius to be from the center to the circumference at the point where the tangent also touches, the circle. We are saying that if you have that concept, we're saying the angle between the two of them, in this case, whichever side, whether it is this side or it is that side, it is always 90 degrees. The angle between the radius and the tangent in a circle is 90 degrees. And that will be our 8th theorem. Very, very important. Please take note of this, because this is also going to help us to build or to introduce another concept very, very soon. So quickly, let's look at the 9th one. We want to be able to finish those theorems so that in our subsequent or in our next lesson, then we can take time to take the theorems and see how we can apply them to solve a typical, say, WAEC question, for example. Okay, so let's look at the 9th one. What does the 9th one say? The ninth theorem says the angle between the chord and the tangent at the end of the chord through one segment is equal to the angle subtended by the chord at the circumference in the alternate segment. Okay, quickly let me put it down for you. Now, the angle between the chord and the tangent. The angle between a chord and a tangent, between a chord and a tangent at the end of the chord, at the end of the chord through one segment, is equal to the angle, is equal to the angle subtended by the chord, at the circumference, let me write it properly, at the circumference in the alternate segment. Quite long, isn't it? Yeah, but it's very, very important. I must say that if you go through your past questions, you are going to find a lot of questions around this theorem. And so I want you to take time to appreciate and understand this particular theorem very, very well. And it's one of the theorems that tends to confuse a lot of students. But I'm going to take time to explain it, so please take time to understand this particular theorem. Take time to understand. So let me put up the diagram. So what are we saying? What we are saying is that if you had a circle, and then remember, I've already introduced the concept of tangent. If you had a circle and then you had a tangent, that is a straight line touching that circle, and you had a chord touching at the point where the tangent is also touching the the chord is touching the circle at the point where the tangent is also touching the circle. Then we are saying that the angle that will be formed here, for example, the angle that will be formed here, and remember that angle goes through. Now this is where the catch is. You notice that we are looking at the angle between the chord and the tangent, but that angle is going through, for example, the minor segment in this case. It's going through the minor segment in that case. Then we are saying that that angle should be equal to another angle which should not be in that same segment, but it should be in the other segment and should be formed by the chord. So in this case, we have the chord, and that chord is not forming an angle in the same segment that we have this other angle, but it is forming another angle in the other segment, what we call the what we are referring to as the alternate segment. The alternate segment. So if this is one, the alternate segment is this one. So the chord is forming, and so we are saying that this angle here, see, the angle A should be equal to the angle B here. So A should be now, very, very important. Please take note to understand this theorem, because there's a lot of questions around it. And as I said, for today we are trying to look at the theorem, so I will not spend my time going through examples on that. But in our next lesson, we will go through a lot of examples, and then I will take time to look at more examples on that one. I'll quickly touch on the very last theorem for the day, and then we'll probably round it up and look forward to our next lesson where we'll look at examples. So quickly, my 10th theorem. One. Now, what does the 10th theorem say? My 10th theorem says the lengths of two tangents from a point outside the circle are equal. The lengths of two, and write it well, two tangents from a point outside the circle are equal. In fact, you should read from points outside the circle are equal. Now, what does that mean? What are we talking about? Let me use this side. What we are simply talking about is that if I had a circle with a center and I had a tangent, a line touching it from this end, touching it here, and another line touching the circle from this other end. Now remember, I've already talked about the angle between a tangent and a radius. So from here, this radius, the angle here is 90, and then from here to there, the angle here again is also 90. Now we are saying that if you do the geometry, if for example this point is say A, this point is B, and this point is C, and this is your center, let's say O, we are saying that these two lengths, the length AB is supposed to be equal to the length BC. Supposed to be equal to the length BC. So that will explain the 10th theorem. Very, very important. So ladies and gentlemen, and in this case, if I'm referring to only Opoku are a student, I'm talking about gentlemen, but I know that other students from other schools will probably have the opportunity of also taking this material and looking at it. But in short, I'm saying that these are the theorems. And you remember in our lesson objective, we said that at the end of the lesson, you should be able to go through, or you should be able to state all the theorems. And so go back and take the opportunity to study and be able to, as it were, verbalize and, as we normally say, write them verbatim. Know them by heart, so that when you see a question, you can actually bring it up and then use it, apply it to solve the questions. So, in short, that will be the summary. And before we go, I'll give you a simple. Okay, so before we we end the lesson today, I want you to take these three questions and go and look at them. So write them, and then in the course of the day and the week, you go through them, and then hope that we'll take it up in our next lesson. So thank you very much for the opportunity. I have been your facilitator, Mr. Clement Kaku Asiedu Menlah. When you have finished, you can probably send your response back to me, or if you have any questions to ask, you can send them to me through my mobile number 0244 591 345. So those are my numbers. If there is any issue, you can. It's also a WhatsApp line, so you can also send me a WhatsApp message, and then we'll look at it. Thank you very much. See you in our next lesson. God bless you.